Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is The Heaviside Cover-Up Method. As always, please be an attentive learner while watching these videos. The cover-up method was introduced by Oliver Heaviside as a fast way to do decomposition into partial fractions. This is an essential step in using the Laplace transform to solve differential equations, and this was more or less Heaviside's original motivation. The cover-up method can be used to make partial fractions decomposition of a rational function, p of x over q of x, whenever the denominator can be factored into distinct linear factors. There are other applications too that we'll talk about. So we first show how this method works on a simple example where we do have distinct linear factors, and then we'll talk about why it works. So example 1, we're going to consider, notice that we've already factored the denominator. We're decomposing x minus 5 over x minus 1 times x plus 2 into partial fractions. Now from the theory, we know the answer will have the form a over x minus 1 plus b over x plus 2. So to determine a by the cover-up method on the left-hand side, this is the left-hand side, we mentally remove or cover up with a finger the factor x minus 1 associated with a. Again, that's what's in the denominator on a. And we substitute 1 into what's left, and that will give us a. So you see we cover up x minus 1, that leaves us with x minus 7 over x plus 2, and we're evaluating this when x is equal to 1. That's the value that makes the denominator of a equal to 0. So when we plug all of that in, we get 1 minus 7 over 1 plus 2, and that's going to be minus 6 over 3, which is negative 2, and that is a. Now similarly, b is going to be found by covering up the factor x plus 2 on the left and substituting x equal minus 2. That's what makes the denominator under b equal 0 into what's left. This gives, we've covered that up, and so we're substituting minus 2. We will get minus 9 over minus 3. The minuses will cancel, and we get b is 3. So thus our answer is that x minus 7 over x minus 1 times x plus 2 is equal to minus 2 over x minus 1 plus 3 over x plus 2. Now, why does this method work? Well, the answer is simple. The right way, the way mathematicians would teach you to do this, is to determine a from equation 1. And that was the original equation by multiplying both sides by x minus 1. And this would give us, so the x minus 1 would cancel here, the x minus 1 would cancel here, and you have this expression because we have to multiply b over x plus 2 as that. But if we substitute x equal 1, what will happen is that this will become 0, which is exactly the equation that we have up here. So the cover-up method, therefore, is just an easy way of doing the calculation without going to the fuss of writing equation 4 out. And it's unnecessary to write the term containing b, again, because it will be 0. And just to generalize this, in general, if the denominator of a rational function factors into the product of distinct linear factors, that means all these exponents are 1, then we can do the same thing because we'll have that p of x, the numerator, over the product of these distinct linear factors. Here we have 1, 2, dot, 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 up to r of them, is going to be all of these a's are, all of these capital A's are, actually all of these a's are constant. But the capital A1 over x minus A1 plus dot, 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 capital AR over x minus AR. And this is listing the distinct linear factors. Then capital A sub I, the numerators can be found by covering up the factor x minus AI on the left and setting x to be equal to a in the rest of the expression. Let's look at an example 2 of this process. So here we're decomposing 1 over x cubed minus x into partial fractions. Now up here, the denominator is not factored into distinct linear factors, but here it is. So factoring x cubed minus x, you first factor out the x, and then you factor, this is the difference of squares. So at the end of the time, you're going to get a product of 3 linear factors, x minus 1, and x plus 1. Well, by the cover-up method, then what will happen is you can determine, and you should do this exercise, but the constant over the x is going to be -1. The constant over the x minus 1 is going to be 1/2, and it's also going to be 1/2 under the x plus 1. And so the real difficulty in this happens really in factoring, and often I will ask you to factor these things. Now, a final comment is the Heaviside cover-up method can also be used when the denominator doesn't factor into distinct linear factors. Now, to be sure, we'll only get partial results, but this can often be a big help. We're going to illustrate this. You end up having to solve fewer and fewer equations than what you were solving before. So, let's look at this. Okay, so suppose you want to decompose 5x plus 6 over x squared plus 4 times x minus 2. Now you see the only distinct linear factor here is this x minus 2. And we know from the theory of partial fractions that we talked about in the lectures that this then is going to be capital AX plus B over x squared plus 4 plus C over x minus 2. But you see, even though we can't use Heaviside on this, we can use Heaviside on this. So if we use the Heaviside method just on C, we can determine C by the cover-up method, and you get that C is 2. But now, instead of having 3 equations and 3 unknowns, you have 2 equations and 2 unknowns. So after you know that C is 2, you can substitute that in, and then A and B can be found by the method of undetermined coefficients. So you're solving 2 equations rather than 3 equations, and that's a reduction of at least a factor of 1/3. So you reduce the work by 1/3. Now, following this plan and using C equal 2, what we do is we combine the terms on the right of this situation 5 so that both sides have the same denominator. That is, we multiply this by this. So we'll know that the numerators have to match in addition to the denominators. So the numerator here of 5x plus 6 must equal, here I have to multiply top and bottom by x minus 2, so this is ax plus b times x minus 2 plus, and then here is 2. And then here I have to multiply 2, but that was what we found, times x squared plus 4. So we distribute and we compare coefficients. So what we'll see when we multiply this is that the coefficient of x squared is going to be a plus 2. But there is no x squared here, so that means that a plus 2 must equal 0. And then we also see that the coefficient of x, which we could check from this. So, and in fact, that's going to be this one is going to be the constant. The coefficient of x is going to be 0, so you're just going to have this. So this is the constant term. It is minus 2b plus 8 is going to equal the constant 6. And so you can solve both those. A is minus 2 and b is equal to 1. And sometimes this is a little bit harder to solve than here. Now, in using this 6 approach, we could have instead compared the coefficients of x. And this is the coefficient of x. That gives us a different equation if we were expanding that. And we say, oh, 5 is the coefficient of x, and we get that. And that's a valuable check on the correctness of our values for a and b. Now, there's still another method that could be used to factor the denominator completely into linear factors. And we could talk about complex coefficients and use the cover-up method, but with complex numbers. At the end, the conjugate complex terms have to be combined in pairs to produce real numbers, and these calculations are sometimes longer, and you need to be good at complex numbers, and we're not going to be talking about complex numbers a whole lot anyway. So, but now a final observation. The cover-up method can also be used if a linear factor is repeated, but there too, it gives just partial results. But again, it is worthwhile getting partial results. You see, if a linear factor is repeated, and let's jump right into our example. Here you see we have x minus 1 whole squared. So that is a linear factor, but it is x minus 1 whole squared. So that, and this is x plus 2. So when we are doing the partial fraction decomposition, we know that this x plus 2 is going to give us c over x plus 2. But x minus 1 whole squared will give us b over x minus 1 and a over x minus 1 whole squared. Okay, well, even though you cannot use Heaviside cover-up theorem to find, well, you can use it for c, but you can't use it to find both a and b, but you can find a, because we're looking at the highest power of the linear factor. So if we cover that up and set x equal 1, you find out that a is equal to 1/3. And finding c, you can cover up x plus 2, and you get c is equal to 9. Now, this doesn't give you the answer for b, but still, you've simplified things now, not by 1/3, but by 2/3. You reduce the work by 2/3. So b can be found simply by substituting things in or solving. For instance, if we put x to be 0, and remember that a is 1/3 and c is 1/9, we can get that 1/2 is equal to 1/3, and this is 1/18, and this is minus b. So we conclude that b is equal to negative 1/9. Now there's other ways to find b, and I leave that to you. But you see the important takeaway of this last example is that the cover-up method works for the highest power, but it's just for the highest power of a repeated linear factor. In the above example, for example, the cover-up method for finding a is just a short way of multiplying the equation all the way through by x minus 1 whole squared and substituting x into the resulting equation. I used my source material. These were some MIT notes that I used in this class and when I teach differential equations. So thanks to them. And Arthur Mattuck is a charming fellow. In closing, now more than ever, time is precious. Each day must count. Do the math. It'll make you strong. And now more than ever, take care of yourself, because self-care is important, and take care of each other, because we're all in this together. God bless you all, and I will see you in class.